Okay, hello everybody. This is a lesson on combining continuous functions, composite limits, and special trig limits. So if f and g are two functions that are both continuous at x is equal to a, then the following combination functions will also be continuous at x is equal to a: f plus g, f minus g, f g, k times f, where k is just a number, or k times g, as well as f over g, so long as g of a is not equal to 0. So this is important because once we know that a function is continuous, right? So for example, any of these combination functions that are continuous, we know that the limit of the function, for example, f plus g as x approaches a, since the function is continuous at x is equal to a, then this is going to end up just being f of a plus g of a, right? So we can use direct substitution. It's going to work whenever a function is continuous at a specific point, right? Let's talk about composite functions. Okay, composite function means we're doing f of g of x, and for a composite function to be continuous, it's a little bit different than just the other combinations that we talked about, right? So f of g of x is going to be continuous at x is equal to a if g is continuous at a and f is continuous not at a but at g of a. These are going to be our tests for whether a composite function is continuous at a specific point. So let's go on to this theorem. This theorem here says that even if the inside function g of x, right, say it's not continuous at x is equal to a, but the limit exists at x is equal to a, right? So if the limit exists and if f of x, the outside function, is continuous at that limit, then the composite function will basically be continuous at x is equal to a. And what that means is that we can pull the limit into the composite. So we can evaluate this composite limit. Instead of doing the limit of f of g as x approaches a, we can do f of the limit of g as x approaches a. But to do that, we need these two conditions to happen. The inside limit has to exist, and the outside function has to be continuous at the inside limit. So for composite functions, in a way, the conditions for the composite function to be continuous are not as strong as for these other functions, because for like f plus g to be continuous, the at x is equal to a, f of a and g of a both have to be f and g both have to be continuous at x is equal to a. But in the case of a composite, if the inside function is actually not continuous, that means it might have a hole, for example, but the limit exists, then we might still be able to have a continuous composite function. Okay, so how does this work in terms of problems? Well, we just check these two conditions and then we do our problems accordingly. So here's a composite function. You check the first condition. Does the limit of 1/2 x as x approaches pi over 2 exist? And it does. That's just pi over 4. And condition number 2 is tan x continuous at pi over 4? And it is, right? So both of the conditions are met, and so I can just do this problem by pulling the limit inside the function. Sorry, what I mean to say is do this: tan of the limit as x goes to pi over 2 of 1/2 x. So this is tan pi over 4, which is equal to 1. Okay. This next one, same idea. Check first the inside limit. That's equal to sine of pi over 2 or 1. E to the x is continuous everywhere, right? So that's clearly continuous at 1. So this just becomes e to the limit sine x as x goes to pi over 2, which is e to the 1 or e. This next one, first condition, limit tan x as x goes to pi over 2. Now this is a D and E. And so if the inside limit is a DNE, and it's a DNE in the way of being a vertical asymptote, right? That's really what's happening here. It's not a hole or anything like that. Then the outside limit, obviously the composite limit is not going to exist, right? So this is going to be a DNE. This next one, let's see, the limit as x goes to 0 of 1 plus cosine x, that's equal to 2. ln x is continuous everywhere for x greater than 1. So it's definitely continuous at x is equal to 2. So this becomes ln of 2. Okay, this one, condition 1, the limit as theta goes to 0 of theta plus cosine theta, that's the inside function, that's equal to 0 plus cosine 0 or 1. And cosine is continuous everywhere. So this, we can bring the limit inside, right? Bring this inside, and we're really doing cosine of 1, right? Cosine of 1 means cosine of 1 radian. You can go into your calculator and find that answer as a numerical number, or in a no calculator question, we just leave it like this. Okay, let's look at the next one. What do we have here? So bringing in, let's check the limit of the inside function at the arrow number. So this is going to be equal to the limit. Let's just do direct substitution. It's going to be the square root of 4 squared minus 2 times 4 minus 4, square root of 16 minus 8 minus 4, square root of 4, which is 2, right? So the inside limit exists, and the outside limit, outside function 3 to the x is continuous everywhere. And so this is equal to 3 squared or 9. Okay, so that's how we do these problems. Now let's move on to some graph problems. So graph problems. Let's see. So here we have two graphs. Oops, this one is F and this one is G. So first of all, again, a lot of composite limits, right? But we're going to look at the graph to get the answer. So let's see here, again, asking ourselves the same two questions. Does the limit of G, the inside function, exist at the arrow number? Well, this is G, so, oh, looks like we have D and E. Oh, it's -2. I went to +2. Sorry about that. So we are actually over here. G, yeah, sure does exist. It looks like it's 3, right? So this is 3. And then I have to see, is F continuous at 3? Yeah, F looks nice and continuous at 3. So those are my two conditions. F is continuous at 3. I would want to see you writing these two conditions down before you do this on your paper, right? Because that shows the reader, the AP reader or me, that you really know what you're talking about. So then we need F of 3, and F of 3 looks like it's -1. Okay, the next one is the limit of G of F at 0. So first checking the limit of F as x goes to 0. That looks like 3. So that exists. And then the question is G continuous at x is equal to 3? Let's take a look at G. Yep, that's continuous, and I can see the answer is going to come out to be 1. So G is continuous. And this is going to become G of the limit of F as x approaches 0, which is G of 3, which is equal to 1. Okay. Let's take a look at G of F as x approaches -2. So limit of F as x approaches -2 is equal to 2. And G, I believe, is not continuous at 2, right? So this is our first situation where G is not continuous at x is equal to 2, right? So does that mean that this overall limit is a DNE? Well, not necessarily. So what we have to do in a case like this, where you see it's the outside function, that's outside function G, right? Not continuous at the place that we're interested. We're going to have to look at how the inside function is approaching 2, right? We're saying that as x approaches negative 2, the inside function approaches 2. Well, let's take a look at that more closely. X is approaching negative 2, and the inside function is approaching 2. It's approaching 2 from values less than 2 and from values greater than 2, right? So now we're looking at what the y value is doing. It's coming from the top and the bottom, right? So that means that this inside here, right, is getting closer and closer to 2, both from the top and the bottom. So then I have to look at what the outside function g is doing to the left and the right of 2, right? So in other words, I have to go here to the g function. Happens as x approaches 2 from numbers below 2, right, and above 2, right? Because that inside function, that's what it's doing. And so when I'm approaching from below 2, I see that g approaches negative 2. And when I'm approaching from above 2, then I see that g approaches 0. So this case, the overall composite limit will also not exist, right? Because I can now write limit of f as x approaches 2 from the left side, that's the green side, the blue side, is negative 1, and limit of, I'm sorry, I should say g, limit of g as x approaches 2 from the right side is 0, right? And so the two are not equal, and so this is going to be a DNE. Okay. Now, you can have a situation like D. Let's look at that, and then things will get clearer. Here, you look at the inside function, and you see that this limit is equal to 1. You see this limit equal to 1. However, notice that you're approaching that 1 only from values less than 1, right? So we're really only approaching 1 minus, so that means that when we look at the f function, we only need to come from one side of 1, right? And there, your answer is going to be 2. So this one, by the way, so the limit of g as x approaches 3 is 1. The limit of f, or actually I should just say it this way, f is not continuous at x is equal to 1, right? So we're not continuous at this number. So we failed that outside function continuity test. However, we can say that since, if you really wanted to write out the justification, you'd have to say something like, however, since as x approaches 3, g of x is always less than 3, we only consider the limit of f as x approaches 3 from the left side, which is equal to, 2. And so the answer here is going to be equal to 2. Okay, let's do another one. The limit of fg as x approaches 2. So the limit of g as x approaches 2, let's see if that, that's a DNE, right? So in that case, now the inside limit doesn't work, right? So this is already a fail. So when the inside function limit fails to exist, then you're going to look at the one-sided limits on that inside function. So 2 plus, right, and 2 minus. And we already kind of figured these out, I think, in the last problem. This one was negative 2 and this was 0. And then you're going to take those numbers and look at the limit of f at those numbers, right? And so the limit of f as x approaches 0 is 3. And the limit of f as x approaches negative 2 is 2. So these two answers are not the same. This and this, right? Not equal, right? So in other words, this overall limit is a DNE, right? What we've really done here, right, this whole thing here is the limit of fg as x approaches 2 from the right, and this one is limit of fg as x approaches 2 from the left, and we've shown that they're not equal, and so the overall limit is does not exist. I know this is a little confusing at first, but the takeaway really is that in piecewise functions, when you fail those conditions for the composite theorem because of a jump, then you want to look at one-sided limits, and you also want to, if it is the outside function that's failing the continuity test, then you want to remember, or you want to examine the approach, right? You look at that inside function limit and you see, am I approaching from both sides, or am I just approaching from underneath or from above? Okay, let's do one more problem here, where this one is a little bit different looking. It's a composite function, but it's not the g and the f in the picture. It's an equation here and the g out here, right? So this equation is a function, x squared plus 2, and this is the inside function. So x squared plus 2 is a parabola that's continuous everywhere. So we expect that when I do this, the inside limit will exist, and that's equal to 3. The outside function is g, and g we know is continuous at 3, right? So that means that this limit does exist, and I can move this inside like that, and I can get an answer of g of 3, which is equal to 1. Okay, let's do a couple more quick problems. We're almost done. So here we have the graph of a function f, and it says, what is the limit of f of x as x goes to -1? Now, remember, you can make a composite like that, f of x. So again, let's just do what we know how to do. Does the limit of f as x approaches -1, does that inside limit exist? Looks like it does. Looks like it's equal to 3, right? So that works. Is the outside function, which is f, continuous at this number 3? Nope, not continuous, right? So now we have this situation that we saw earlier. So we're going to look at the approach. Notice the approach here. The approach of the inside limit is from below, right? So only from below. Approach to 3 from numbers less than 3. So that means that when I look at the outside function, I can approach it just from the left of 3. So I can really look at the limit of f as x approaches 3 from the left only. And that certainly does exist. That answer is -1. So the overall answer here will be -1. Okay, let's see, what else do we have? And look at what. Okay, we're done with composite limits. Very quickly, I want to tell you about two special trig limits. One thing I want you to remember, by the way, in calculus for trig is that you are always in radian measure. We are never counting in degrees, always in radians, right? And because none of our formulas like these limits or other things you're going to learn work in calculus unless you are in radians, right? So okay, so here we are in radians, and I want you to remember a special limit. Just memorize it for now. The limit of sine x over x as x goes to 0 is 1, okay? This is a graph of sine x over x. You can see that, you can't really see, but if you were to zoom in here, you would find there's a hole up there because x cannot be equal to 0. And then this graph is very common. It's used a lot in science and engineering. It's this sine function looking like thing, but it kind of, the oscillations get damped out or smaller and smaller to the two sides, right? And the limit of this graph as x approaches 0, you can see that the limit approaches 1. So remember that. And then another one important function as well, 1 minus cosine x over x. And that's this graph right here. And again, there's a hole here, but you can see that the limit as x approaches 0, this function approaches 0. So remember these two special trig limits. I'm not going to take the time to prove those to you now because later on in the course, I'll be able to prove it to you very easily. And so I figure for now, just take it based on the graphs, but later on we'll prove this with some algebra as well. Okay. So what are our takeaways from this lesson? The takeaways are focus on composite limits. And when you have a composite limit, you can move the limit inside and do f of the inside limit if two conditions are valid. And those two conditions are that the inside limit exists at the arrow number, and or actually let's say it the way we said it before, this is b, some number, it exists, and then f, the outside function, is continuous at x is equal to b. Okay, if you are evaluating this composite limit and g of x has a jump discontinuity at x is equal to a, or if f of x has a jump discontinuity at f of g of a, then we're going to need to check the one-sided limits before we make any conclusions. True or false? If the limit of g of x as x approaches a does not exist, then the limit of f of g of x also does not exist. If false, provide a counterexample. So try to pause the video and see if you can come up with a counterexample, or is the statement true? Let's see, I could make up a counterexample like this. I could do, okay, here's a g of x limit that doesn't exist at x is equal to a. And then if I say that this is equal to 2 here and this is equal to 4 here, so this is g, right? And then I can make an f function where the limit of f of x as x approaches 2, say that's equal to 1 maybe, or 2 even. No, let's make it 1 just to have some different numbers in play here. So this limit as x approaches 2 is equal to 1, and then the limit as x approaches 4, right? I could also make that equal to 1. I could even do this, right? So here's a simple function where the inside limit of g of x as x approaches a, that's clearly a DNE, right? But the left and right limits exist here, and those are 2 and 4. So then when I do the limit of the composite function and I look from the left, then I'm going to be doing, the inside goes to 2, and so f is going to go to 1. And the outside, if I do x approaching 2 from the right, then I'm going to 4. So then on this graph I have to go to 4, and actually I only have to go to 4 from the greater than side, right? And I only have to go to 2 from the less than side. And anyway, both of those are 1, the way I drew this graph, right? So that might have been an overly complicated example, but the point is, just because the inside limit doesn't exist, it doesn't mean the overall limit doesn't exist. And also just because the outside limit, just because the outside function is discontinuous at the value that we're talking about, that also doesn't mean that the overall limit doesn't exist. Okay, special trig limits 1 and 0. And yeah, that's all I have for you.